Hello and welcome back, and if you are new here, welcome, we are very glad to have you here. In this episode of Season Series, we are continuing our story about PN junctions, semiconductors, and diodes, as unavoidable prerequisite to our main goal, transistors and amplifiers. If you have not already seen the previous episode, we strongly recommend to do so, because we are going to lean heavily on topics covered in that episode, and knowledge we have gained, and what we have learned about silicon and germanium atoms, valency, creation of covalent bonds, valent electrons, creation of p and n-type materials, formation of PN junction, and so much more. In today's episode, our attention will be focused on expanding our knowledge more about PN junctions, forward and reverse biasing, diodes, and we will show some examples of their roles in electric circuits. So, let's begin. First, let's define diodes. In simplest of terms, a diode is a device that allows electric current to flow in one direction, but blocks it in the opposite direction. Historically, several names are associated with discovering and observing some of the characteristics of today's modern diodes. From Ferdinand Braun in 1874, who found that some crystals, such as galena or iron pyrite, could conduct electricity in one direction when connected to a metal wire, to John Fleming in 1904, who invented the thermionic diode, or vacuum tube diode. This was a glass tube with two electrodes, a heated cathode and a plate. Fleming used this device to convert alternating current to direct current, and to detect radio signals. Modern diodes started with the development of semiconductor in the 1930s, when scientists discovered that some materials, such as silicon or germanium, could form a junction between two regions with different types of impurities, p-type and n-type. This junction, called a PN junction, had similar properties to a crystal rectifier, but with better performance and reliability. The first semiconductor diode was made by Russell Ohl in 1940, at Bell Labs. Diodes are now widely used in electronics for rectification, modulation, switching, signal processing, and more. Main role of diode in electric circuit is to allow flow of current in one direction and block the flow in opposite direction. Diodes have two terminals, or simply said, two connectors. One is called anode, and the other one, cathode. Anode is connected to positive terminal of power source, and cathode is connected to negative terminal of power source. That also means that diodes have poles, which implies that it is very important how we orientate diode in our circuit. In general, anode always has to be connected to positive terminal of power source, and cathode to negative. If reversed, diode will not function as expected, or it may function, or better said, will malfunction in quite unexpected, and sometimes, destructive ways. Diodes comes in many shapes, sizes and types of encasements. They can be encased in glass, plastic, ceramic and etc. As a rule of thumb, no matter the form, on the body of the encasement, in general, there will be a white or black line, indicating that the terminal closer to line is cathode. In electric circuits, diodes are represented via right-pointed triangle, with a bar on right side. Bar indicates cathode connector. Depending on type of diode, other symbols can be used to depict diode in electric circuit, for example, Zener diode, Schottky diode, avalanche diode, LED diode, and etc. Each of them has specific characteristics, and performs specific role in electric circuit, but what is common for all of them is that they have to be properly orientated in circuit. From previous episode, we have learned how P and N-type materials are made by doping silicon or germanium crystal lattice with trivalent and pentavalent dopants. As a result of doping process, a PN junction is formed, and that PN junction is basis of principle of how diode works. As an emergent property of formation of PN junction, an electric field is formed. We have also learned that dormant extrinsic semiconductor acts as an insulator. In order for it to become conductive, it has to be exposed to external force, in form of voltage, of 0.3 or 0.7 volts, depending whether germanium or silicon crystal is used in manufacturing process. Now, let's dig deeper into what happens when we put a diode in a circuit, and let's observe what happens when we provide certain conditions, required for diode to function. First, a warning. Before you try to implement diodes in your circuit design, please be aware of one very important characteristic of diodes. Diodes are not resistors, and we repeat again, diodes are not resistors. The role of diode in electric circuit is to regulate the direction of current. Diodes do not regulate intensity of the current, nor they limit the amount of current flowing through the circuit. Placing diode in electric circuit without resistor, or some other type of load, represents a short circuit. Short-circuiting a power source is extremely dangerous, and should never be implemented, under any circumstances. We repeat again, diodes are not resistors. Diodes regulate direction, not intensity of current in the circuit, nor do they limit the amount of current in the circuit. Now, that's out of the way, let's build ourselves a simple circuit. Consisting of power source, a simple diode, and a LED diode, which will represent a load. We will also need a resistor, in order to limit the amount of current flowing in our circuit. Choice for the resistor will be determined by the maximum current allowed for the LED diode, which is 20 milliamperes. Also, the choice for the power source will be determined by voltage drop requirements for each and every component in the circuit. First, we will have to look up requirements for our LED diode. From our resistors video, we have learned how to read and interpret specifications datasheet for LED diodes, and determine circuit requirements. Since we will be using red LED diode, the forward voltage from specs is 2.2 volts, and maximum sustained current is 20 milliamperes. We have also learned that LED's forward voltage is just another name for voltage drop across LED diode. We have defined a voltage drop as a measure of internal resistance, with which LED diodes pushes against power source. With known parameters for desired current, voltage of power source, and LED diodes voltage drop, by using simple formula, we were able to calculate value for the current limiting resistor for our circuit. But now, beside the LED diode, we have another component to take into consideration for our calculus. We also have to include a voltage drop, the diode itself. Of course, the necessary information should be provided in specifications document for the diode, either from the manufacturer or the seller, accompanying the purchase of diode, or by just simply looking up the specs on the internet. First, we will look for info about diode in datasheet. Later in this video we will demonstrate some other ways you can determine orientation and voltage drop of the diode using multimeter. Now, let's display our datasheet and see what all of this gobbledygook means. We are looking for section named electrical characteristics, and we are especially interested in voltage drop across diode, so we could do our math and determine value of power source and resistor for our circuit. Now, one would assume that first order of the business is to find and read electrical parameters we are looking for in our datasheet. And one would be wrong. As the old saying goes, the devil is in the details, sometimes called small print, or in our case, in the note below the table containing data. From the language reserved and understood only for and by the top scientific minds, to everyday language used by us, mere mortals, this highlighted note says, parameters listed in the table above are for very specific usage scenarios and obtained under special test conditions. Again, simplified even more, note says that the data from the table are not applicable and transferable to your everyday usage of this product and your circuits. Also, in next row, there is an asterisk mentioning JEDEC registration data. We will ignore this line for now, as it is not important for our goal. Let's decipher the first data row from the table. It says, maximum instantaneous forward voltage drop, and then some other remarks in parentheses. This parameter tells us the value of voltage drop across the diode, or as this parameter is scientifically called, forward voltage drop, at the instant the circuit is powered on. It says that typically, or plainly said, usually, or, in average, this value is 0.93 volts, and the maximum measured value is 1.1 volts. Now, here comes in play that note from before, and additional remarks in parentheses. What these remarks parentheses tells us is that these values are obtained under the following test conditions. First, in the moment when the circuit is powered on, the power source provided current of 1 ampere running through the circuit. This parameter is marked IF, which stands for instantaneous forward current, and at the time of the test, the junction temperature was 25 degrees Celsius. Again, simplified, this says that ambient temperature in the laboratory was 25 degrees Celsius, and that all of the components, including the diode itself, were at room temperature at the time the test had been conducted. This parameter is marked TJ, which stands for junction temperature, where term junction describes the contact points of the diode with the rest of the circuit. In summary, when the circuit is powered on, the peak of the forward voltage drop in that instant of time will be somewhere between 0.93 in average and 1.1 volts at maximum. Next parameter is called maximum full cycle average forward voltage drop, and then some other remarks in parentheses. Now, this is the parameter we have been looking for. We want to know what is voltage drop across the diode in our circuit, so that we can calculate the value of resistor R, so that we could have continuous current of 20 milliamperes flowing through our circuit. This specific parameter is obtained at very unique laboratory conditions listed in parentheses. Let's look at them closely. First, we have I/O, which stands for operating current. Simplified, this says, constant current of 1 ampere flows through the circuit at all the time, while circuit is powered on. Next is TL parameter, which stands for leads temperature. When current flows through the circuit and the diode will get hot. Remember from before, voltage drop is a measurement of internal resistance of the electric component against the power source. Since our diode has that measure of specific internal resistance, it has to dissipate generated internal heat. Some of the heat will be dissipated through the body of the diode, but some will be dissipated through the leads connecting the body of the diode with rest of the circuit, via junction points. Conclusion, this parameter is obtained under test condition, where measured temperature of diode's leads was 75 degrees Celsius, and the leads are exactly 1 inch, or 2.54 centimeters long. The obtained value for forward voltage drop parameter is 0.8 volts, maximum. Now, this is really infuriating. First of all, we don't have average voltage drop, we only have information that when the circuit is powered on, and current flowing through the circuit is 1 ampere continuously, the voltage drop across the diode will not exceed 0.8 volts. Great! There is no way to tell from this table what the voltage drop will be if the current flowing through the circuit is our desired 20 milliamperes. As you can see, the typical value is missing. All this exercise was for absolutely nothing. It gets more and more frustrating as we go on. Next parameter in our table is called maximum reverse current, and this time, the manufacturer didn't even consider to grace us with the value 4 rated DC voltage for this parameter. So, we will have to infer that this specific parameter was obtained when DC voltage was circled from 0 to maximum volts allowed for this specific diode. In our case, we are using 1N4001 diode, and its rated maximum operating DC voltage is 50 volts. Fortunately, this parameter is listed in another section of Datasheet. So, what does this all tells us? It says that, when we flip the diode, or simply put, we change the polarity of the diode, connecting anode to negative, and cathode to positive terminal of the battery, or DC power source, there will be a certain amount of current flowing through the circuit. At room temperature, the parameter Tj equals 25 degrees Celsius, that current will typically be 0.05 microamperes, and it will not exceed 10 microamperes. Remember from before, Tj stands for junction temperature. Next row says that when junction temperature is at 100 degrees Celsius, for example after the very long test run, the typical current flowing through the circuit will be 1 microampere, and will not exceed 50 microamperes. Let's simplify this. The entire point of the diode in circuit is to prevent flow of current in undesired direction. If by mistake, we install diode the other way around, so that the polarization of the diode does not match polarization of the battery, one would expect that there will be no current flowing through the circuit. This would be the case. Diode is what is called an ideal diode. Since there are no ideal electrical components, and in our case, there is no ideal diode, if we install diode incorrectly in the circuit and power the circuit on, there will be some small amount of current flowing through the circuit, nevertheless. Since the reverse current is so small, it measures in range of 10 to the power of -6, for all practical purposes, in most circuit calculations, this parameter is simply ignored. Last parameter from our table is called maximum full cycle average reverse current. This parameter is closely related to the parameter above, in sense that this parameter tells us not typical and maximum reverse value of the current at peak DC voltage at specific junction temperature, but rather tells us the maximum average value of reverse current under continuous working condition. The laboratory test parameters at which this value was obtained are as follows. The circuit is continuously running for long period of time, with constant current of 1 ampere flowing through the circuit, and the temperature of diode leads is at 75 degrees Celsius, and the measured reverse current through the circuit is averaged, and not exceeding, 30 microamperes. Now, we would be negligent if we do not point one very important point of confusion. For someone who is new in all this gobbledygook about electronic circuits, the term reverse current could suggest that the current is flowing in the opposite direction. No, in DC circuits the current always flows from positive to negative terminal of power source. This is so-called an engineering direction of flow of current. In this scenario, the above-mentioned reverse current parameter does not mean that current is flowing in reverse direction, from negative to positive terminal of the power source. The term reverse addresses the reversed orientation of the diode itself. Simply put, in this context, reverse mean that we flipped the diode and connected it the wrong way around. This is just another in myriads of poor naming examples used in theory of electronic circuits. Now, after all this run through the electrical characteristics section of the datasheet, we still do not know what is the voltage drop across the diode at 20 milliamperes of current running through the circuit. There is another section of datasheet that might give us some information about our query. We will now take a look at typical forward voltage graph. This graph aims to tell us the value of typical forward voltage drop, but x-axis is labeled as instantaneous forward voltage. Just a few moments ago, we have learned that these are two very different parameters, obtained at very different laboratory test conditions. So, not only that the manufacturer didn't provide us with more useful information about the product, but he even didn't bother to pay enough attention to name the graph and x-axis correctly. Since y-axis is labeled from 0.1 to 10 ampere, we cannot read from the graph what would be voltage drop at 20 milliamperes. The lowest value presented in the graph is 100 milliamperes. This graph is another colossal waste of time. Since we have not found the required info in the datasheet, there are still a few options on how to get that elusive diode voltage drop value. At the beginning of this video, we have mentioned that typical voltage drop for silicon diode is 0.7, and for germanium diode is 0.3 volts. Now, these parameters are from so-called ideal diodes, respectively. Now, some of you watching this video might wonder why all this fuss about voltage drop, why not simply assume 0.7 volts and carry on? This is a valid point, but more often than not, you will find yourself in situation where you do not know what type of diode you have. Most general-purpose diodes are very small and do contain not readable markings on their body. Even with magnifying glass, it can sometimes be very difficult to read the markings, and when diode is old and scratched, it is impossible. So, it is prudent to learn a couple of different ways to test and identify diodes. Before we do that, let's just recapitulate what we have learned so far. The main function of the diode in electrical circuit is to allow flow of the current in only one direction. Diodes have two connecting point, anode and cathode. Connects to positive, and cathode to negative battery terminal. Diodes have internal measurement of resistance to the flow of current from power source called voltage drop. If installed incorrectly in the circuit, there is a small but negligible current flowing through the circuit. Another two very important parameters for diodes are maximum DC voltage and maximum current ratings. If you exceed any of these two parameters, the diode will blow. Now, let's see how we can determine voltage drop by using multimeter. On your multimeter, try to locate this icon. Depending on type of multimeter you have, it may be at another location, but in general, every multimeter has this option for selection. When selector is in this position, it allows a small current through the diode and measures voltage drop across the diode, against predetermined voltage. The display will show voltage drop in millivolts, for this specific type of multimeter. We have measured the value of 676 millivolts, which rounds up to predicted 0.7 volts for general-purpose silicone diode. If you would like to see a more detailed video on how to measure voltage drop across the diode and determine values of voltage and current in this test setup, please leave a comment below. Another way to measure voltage drop across diode is to create simple circuit consisting of DC power source and diode and resistor in series. If your multimeter does not have a diode measurement setting, and can only measure voltage, or perhaps, you have another way to measure voltage, this can be a simple way to measure voltage drop across the diode. For example, DC source is 5 volts, resistor is 220 ohms, so the current running through the circuit would be 20 milliamperes. This setting ensures that no diode or resistor would overheat. As you can see, we get value of 710 millivolts, which rounds up to predicted 0.7 volts for general-purpose silicone diode. The discrepancy between multimeter testing and test circuit readout is due to difference from two different DC sources, and value for current flowing through the circuit. The UI characteristic of the diode is not linear, so this discrepancy is to be expected. So, we can now return to our original circuit and finally calculate the value of resistor R. Using all we have learned so far, let's plug in some numbers. We have 5 volts DC source, and we have measured voltage drop across the diode to 0.7 volts, and we know from before that voltage drop across the LED diode is 2.2 volts, and we want 20 milliamperes of current running through the circuit. Using the formula on the screen, we can calculate that we need resistor with resistance of approximately 105 ohms. Since 105 ohms resistor is not a standard value, we will use next best value of 100 ohms. It is a rule of the thumb to round up to the next upper closest value, but in this case, the difference of 5 ohms is within acceptable margin of error. By using appropriate components, we have built a test circuit on breadboard. We have measured the current flowing through the circuit. The measured value of the current is 19.8 milliamperes, so our calculations are okay, and within acceptable margin of error. There is just one thing left to do, and that is to give appropriate definition for diode biasing. Diode biasing refers to the application of an external voltage across a diode to control its operation. It essentially determines whether the diode will allow current to flow or block it. There are two primary types, forward and reverse biasing. Forward biasing allows current to flow through the diode. This is achieved by connecting the positive terminal of a voltage source to the diode's anode and the negative terminal to its cathode. Reverse biasing blocks current flow through the diode. This is achieved by connecting the terminal of a voltage source to the diode's cathode and the negative terminal to its anode. This concludes our introductory video to semiconductor components. In our next video we will explain the difference between natural and engineering direction of electric current in circuits, so stay tuned. Please, before you leave, show your appreciation by liking this video, sharing it, leaving a comment, and consider subscribing. Thank you, and see you next time. Bye.